Welcome on section 4.4. We're looking at the fundamental theorem of calculus today. We're going to do day 1. It'll take us a couple days to get through this. And you can kind of see there are 4 big ideas that we're going to introduce in this particular section. We've worked with derivatives, and now we're really on this integral side where we talk about the area between the curve and the x-axis. So, today's focus is the fundamental theorem of calculus, a major topic for us in calculus, often known as the FTC. And let's just read it together. If little f is a continuous function on the closed interval from a to b, then capital F is an antiderivative on a to b. Then we can say that the integral, the definite integral, because we've got lower limit of a to upper limit b, is equal to capital F. And remember, capital F is this antiderivative. So how do I get from little f to capital F? I integrate to get there. So I'm going to find the integral of little f, which will give me capital F. And then the straight line means to evaluate. I'm going to evaluate this antiderivative from these two numbers, from the lower limit a to the upper limit b. That calculation looks like this. I take my integral and I evaluate it at x equals b, and I also evaluate it when x equals a. And I find the difference between those values. So instead of having to do the area under some curve, and we use those rectangles to do that, we now have a method of doing the calculation and not having to draw the picture and use rectangles. One thing that you're going to find helpful is to totally have the derivatives and antiderivatives committed to memory. So if you are not at that point yet, please practice it on your own. Take a snapshot of this, print it again, and keep going over and over on that. I'm going to pause for a moment and have you fill this in. Okay, we are back together. I hope you hit pause and try to do it from your memory. Why don't you double check and make sure that everything is accurate of what you wrote down. And pay particular attention, of course, to negatives and where they come into play, as well as, this is kind of a new one. We have not hit this, but I think you can make the leap to knowing that the derivative of natural log is 1 over x, therefore the antiderivative of 1 over x becomes natural log x. What you need to do, though, is insert this absolute value to keep x as a positive value, because natural log is only defined on the positive values of x, and not 0, so it's got to be greater than 0. Okay, so let's just introduce this fundamental theorem of calculus and go for it. First thing I'm going to do to my function is I'm going to integrate it. And you know how to find integrals. We've worked with that. So we're going to take negative 2x and raise it a power. So that gives us a power of 2 divided by 2 plus 3x. Now, instead of writing plus c, because we are not in an indefinite integral anymore, we are on a definite integral, we're going to write that evaluation sign. I'm going to evaluate this from negative 2 to 1. This right here is really acting as our capital F of x that we had talked about, right? It is the antiderivative. Let's simplify it before we go on. So 2 over 2 cancels and we get negative x squared plus 3x evaluated from negative 2 up to 1. Now what I need to do is this second portion. I need to evaluate that capital F function at these two values and then subtract. So I'm going to move down here, and my first one I'm going to do is my f of 1. So plugging in 1, because you start at the top, negative 1 squared plus 3 times 1. That is that first evaluation. And then it says to subtract. So I'm going to hit subtract. The next portion, and that would be when f is at negative 2. So I want to evaluate at f of negative 2. Remember how it was b minus a, and this is a b value, this is the a value, the lower limit. So we're on the lower limit, throw in negative 2, we get negative of negative 2 squared plus 3 times negative 2. I encourage you to write that out. Do not try to do too much in your head. That is when errors happen. So -1 plus 3 minus, I'm going to take a moment and just work with inside my parentheses, then give me a -4 minus 6. That looks like -10, but a negative outside makes that +10, so I've got -1 plus 3 plus 10. That gives me 13 minus 1. Looks like we're coming in with 12. The area under the curve should be 12. And so now what we're going to do is we're going to double check using our graph to the left here. We want to go from -2 to 1. So we're talking about this region right in there. This integral should represent the area on that, shouldn't it? So let's just double check that. We've worked with that. I can recognize that that is a trapezoid right now. So let's use the trapezoid formula to check out this area. Area of this trapezoid. It has 1/2 the width is -2 to 1. That's a width of 3. My height on the left side is 7. My height on the right side is a 1. So height on the left plus height on the right, and that would give me 8 times 3 is 24. 24 over 2 gives us 12. Well, looky there. They match up, and that is a good thing because that's what should happen. I would like you to try B on your own. Use this fundamental theorem of calculus idea to evaluate it. We've already gotten the integral, haven't we? We've worked that, and we're working the same thing. So what I would like you to do is take that -x plus 3x and evaluate it now from 0 to 5. So hit pause and do it. Okay, so I went ahead and calculated it while you were doing it, and I got -10 for my answer. If you did not end up with that, please double check. You remember what you had to do was evaluate at 5 and evaluate that capital F function at 0, your antiderivatives, and get that. I also double checked. I went over to the left and looked at the area representation of this integral, and I ended up with two regions, one being a positive region. Up here we know this is positive, and we know that this is going to be negative area, and I did the two calculations, the height times the base and the height times the base, and it too checked out to give us the same values. Down below, I have several that we can go through. I would like you to get your calculator out because we are going to show you also, or I'm going to show you how to calculate definite integrals on your calculator. So you can use that as a verification. Let's do this first problem here. What we need to do is integrate first, correct? So I'm going to take x cubed, raise it by a power, divide by that new power. And I don't put the plus c down because we aren't working with an indefinite integral. We have a definite integral. We can get a numeric value. Evaluate this from 1 to 3. So remember, this is your big capital F coming out. The derivative of that sits back there, doesn't it? So let's go with evaluating this thing at 3, the upper limit minus the lower limit of 1. And that means I'm going to have 3 to the 4th divided by 4 minus 1 over 4. When I put in 1, that's going to give me 81/4 minus 1/4. And that will turn out to be 80/4, which is equivalent to 20. Now let's check with your graphing calculator. Okay, so you've got your graphing calculator. We can calculate definite integrals using our graphing calculator. It is located in the couple spots. You can see underneath here I've got, you can do it from the graphing screen, the y equals, or you can do it from the home screen. So let's do it from the home screen first. If you hit math and then option 9, you'll notice that that is the function int, or it's calculating the numeric integral. So I'm going to go from 1 to 3. If you have a TI-84, yours should look like this if you have that newer software loaded, which most of you do. If you don't, please see me. Let's get it up to date. So I just put it in like I see it and hit enter, and it couldn't be more easy. It spits out the number, which is 20, and that's all great. If you have a TI-83, here is the instructions for that. You still go to Math 9, but you've got to key your function inside these parentheses. So you'll key x cubed, and then you'll put x, because that is with respect to x, like we did right there, and then comma, lower limit a to upper limit b, which is 3. So your screen will look like that, and then hit enter, and you should get your answer. Okay? Also, we can do this graphically like I mentioned. So if you go into your y equals key, load in the function x cubed. I worked with my window a little bit to get it just right. I went from -2 to +3 for my x values, counting by ones, and then my y values went from -2 to 30, counting by tens. That will give me a picture that looks like that, a good portion of that cubic function. Now, if you go to second and calculate, you're going to find an integral calculation there, option 7. And then notice what it's asking us on the bottom of here. It's asking us for the lower limit. My lower limit was 1, so I'm going to key in a 1. And I don't want to write on top of there. Okay, so I key in 1, hit enter. And then it asks me for my upper limit, which is 3, so I hit 3, and it's going to show us the region, and that too came out to be 20. Let me get it a little larger. So there's the area under the curve, that is 20. You can use either method that you would like to do that definite integral on your calculator. Let's get D set up. So I want to integrate this, and I think the easiest way to integrate that would be to rewrite, and maybe I'll even bring this 3 out front, x to the 1/2 power dx. Bring the 3, bring it along, and the integral of x to the 1/2 will be x to the add a half, or add a 1, and I'll be at 3/2. Divide by that 3/2, which is like multiplying by its reciprocal, 2/3. And then I want to evaluate this from 1 to 4. Canceling these 3's makes this process a little bit easier. I have 2x, and then the 1/2 power means the square root, and then cube it, evaluated from 1 to 4. Once again, we take capital F of 4 minus capital F, evaluated at 1. I'm going to have 2. Square root of 4 is a 2, and then I've got to cube that, minus 1 going in. That'll be 2. Square root of 1 is 1. Cube it, it's still 1, so I end up with 2 times 1. And that will be 8. 8 times 2 is 16. 16 minus 2, it looks like we get an answer of 14. Please verify it on your calculator. We can do trig functions just as easily. So go ahead and integrate this, and hit pause and integrate that, and then come back and check to see if you did it right. Okay, hopefully you got your integral right. Now let's do the fundamental theorem part of it, where we evaluate the lower and upper bounds. Starting at the upper bound, I'm going to do the function evaluated at pi. That's going to give me a pi squared plus sine pi. There's my first evaluation minus my second grouping where I evaluate at 0. That's a 0 squared plus a sine of 0. I do encourage you to write some of this out. That'll give us pi squared. That's a 0, isn't it? This is 0, and sine of 0 is 0. It appears that we have nothing more than just pi squared. If you put it in your calculator, please do. Verify that it's right. See that you can do the numeric integration on your calculator. You should get about 9.8696. Letter F. The integral of this, I would take a moment and rewrite this so that I get 2x over x squared plus 3 over x squared dx. I'm going to rewrite one more time to help myself. That's going to be an x to the -1, and then I've got a 3x to the -2 dx. Go ahead and integrate, and then try your fundamental theorem. See if you get it right. Okay, I did my integral, And I came up with 2 natural log of x because this is x to the -1 power. Notice if you add a power and divide by that, you get 0, right? This goes to 0, divide by 0. That should tell you right there that there's an issue. I cannot just simply use the power rule. And the reason is because this is a natural log integral. So when I have 1 over x, the integral of 1 over x is natural log x, and that's what we're sitting with there. So I got 2 natural log x, absolute value of that x, keep it positive, minus 3 over x, evaluated from 1 to 4, and then I went into doing the fundamental theorem, evaluated at 4, evaluated at 1. Notice here you get the natural log of 1, but that is equivalent to 0, so that just popped out. I got minus minus, which gave me a plus 3. And then I rewrote 3 into fourths, so I had 12 fourths. 12 fourths minus 3 fourths ended up giving us that 9 fourths. And there's our answer. I could keep on doing these. I'm not sure it's totally necessary. I'm going to show you how I would approach this problem here. I would think of this as the square root of 2 over the square root of x dx, just to help me integrate this a little bit more easily. That square root of 2 could come out front. It's a multiplier. The square root of x is on the bottom. That would be a negative 1/2. And then we could go into our integration, and that would turn out to be the square root of 2 times x to the positive 1/2 divided by 1/2, which is 2 over 1, right? And then I want to evaluate it from 1 to 8. I would have square root 2 out front, and then I'm going to put my 8 in. I'd have 2 square root of 8 minus, put now the 1 in, 2 square root of 1. And I feel like I've lost a 2 along the way somewhere. Oh, no, there, it's all good. Here's my 2 I was looking for. So I'm going to have square root 2 times 2 times, break down that root 8, and we get a 2 root 2 minus 2 root 2. That was just purely distributive. Should have called it square root of 16, shouldn't I? We're going to get the same answer. I'm going to have 4 times a 2 there minus a 2 root 2. So I get 8 minus 2 root 2. Done. On this one, I would expand that squaring, and that's going to be a 4x squared minus a 4x in the middle plus 1 at the end. Integrate, do the fundamental theorem. I think you're going to find that the answer comes out at 14/3. Now, let's go to this last area. Actually, before I do that, I'm going to break this into a separate video.